Although Magdalena will say something a bit different. And it started with the collaboration of Magdalena, probably you all know Magdalena, who was then professor at the Department of Physics at Silvestre in Mexico City, and collaboration was with Professor Dhont of the University of Constance. So this collaboration was with the time growing. People in the group of Professor Klein spread across Germany. Many people who participate in this collaboration from the Mexican side also spread in Mexico, many places. Magdalena moved to San Luis Potosí. I also moved to San Luis Potosí. But this is, let's say, a long time collaboration with these people who emerged from these two groups and now are located in different places. So this is the story of this collaboration of about 40 years. Let me say something about Professor Dhont. What I would say, he wrote himself, so he sent a short CV. He doesn't want probably to say all his achievements or his career, which is long, so I would say this very short few things. So after an education as a laboratory assistant professor, Dhont.
Oh, it's not a profession.
Assistant, a laboratory assistant.
To do all the work by hand.
Yes, you were the assistant. Professor Dhont started to study chemistry at the Utrecht University in the Netherlands. During his chemistry study and the subsequent PhD from 1981 to 1985 in physical chemistry at the Frankfurt laboratory of the supervision of Ingenious Frank, he gradually shifted his interest to physics. So he made a right move. Physics. No. This resulted in a postdoc from 1985 to 1987 at the Constance University under the guidance of Prof. Klein at the University of Constance. It was in this period when he was postdoc in the University of Constance, is when he met Magdalena and Henry and also Gerhard. So it was the melting pot this place in Constance. He then returned to the Frankfurt laboratory as an associate professor in the physical chemistry group headed by Henry Gerhard, and then moved in 2000 to the Research Center Zurich and the Heinrich University in Düsseldorf, Germany. So he was also at some point general director of this research center in Zurich. So we are honored to have you here, Jan. So please proceed to the talk. I don't have the title.
No, there are three titles. So if I do it without the microphone, can you understand me? So hear me in the back?
I think you read it for the Zoom.
It may be useful for the Zoom people that are online.
Okay. Well, thank you very much. Well, so Gerhard and myself are making a tour in Mexico. And I really appreciate and I'm really honored by the people who organize all this. I want to also thank Magdalena for using the meeting I understand. So I'm going to talk about colloids. And Magdalena asked me to explain a little bit what colloids are. So I think that not everybody in the audience explained it to colloids. So I will give a full introduction to colloids. And then I will talk to about phase transition and the creation of a dynamical state that is induced by applying an external electric field in suspensions of highly charged like hollow. And I will finish then with the formation of glass in these kinds of systems at very high concentration. So let me start by explaining what colloids are. So colloids are actually nothing but very big molecules. There are so aggregates, you could say, with linear dimensions in the time range of a few nanometers to a few microns. So they should be small enough in order that they exhibit thermal motion. So that the thermal motion of the big colloidal particles, the big molecules, is of course reduced from the collision of those molecules, so a colloid is embedded in the fluid, typically water. And of course, the water molecules collide with the surface of this colloidal particle. And if this colloidal particle is small enough, that will result in erratic motion, which is nothing but the thermal motion of the big thing, which should not be too big, because then the thermal motion ceases to exist. That's then the thermal motion makes this thing a normal molecule. So it should be small enough, not larger than 10 microns approximately. And you can see here that so this was found for the first time by Robert Brown about 200 years ago. So this motion is also called Brownian motion, but it's nothing but the thermal motion of this big molecule. So you can actually see this thing. So this one sphere with a diameter of so half microns. So you can see this in the simple microscope. And this is simply the thermal motion of the molecules, which Robert Brown observed almost 200 years ago. And there are many examples of colloidal particles who have inorganic colloids, a little suspended range of a few microns, for example. There are many biomicromolecules who belong to the colloidal glass. So, like proteins, for example, the viruses belong to colloids, and actually entire bacteria as well. They have a size approximately which is below the 10 microns. So even some bacteria show the motion, and you could call them also colloids. Now, of course, you have different shapes. You can have squares, as you saw in the movie. You can have rod-like, flexible colloids. You can have plate-like colloids, for example, in paint. And even a polymer you could consider to be a colloid. So it's a very large class of particles, with the size that does not exceed 10 microns. Now, at the same time, it should be larger than 2 or 3 nanometers. And the reason for this is that you want to treat the solvent as a continuum. So let me first say that the Brown motion is affected not the thermal motion of the big molecule. So you can apply the same laws of thermodynamics, physical physics to these molecules that you know for small molecules. And they show just like the normal systems of opacity. So you don't have to learn anything new when you understand the behavior of colloids, except that you have to learn about hydrodynamics. So these things are large compared to the size of the two molecules, and that makes it possible to describe the interactions between two colloids mediated by the molecules of the fluid by hydrodynamics. So they should be large enough that you can describe the hydrodynamics. So if this colloidal particle moves in a certain direction, so like you can see here, if it moves in a certain direction, it's induced a fluid flow field. Being a macroscopic object, being much larger than the size of the fluid molecule, and that fluid flow field propagates to the second particle, which of course affects this particle in its motion. So you have direct interaction as well, of course, example, the simplest parent electric potential V as a function of the distance between the center of the soft to the simplest electric potential is the so-called hardcore or excluded volume interaction, where you have two cores that cannot overlap, so they do not interact, they don't touch each other, and as soon as they try to penetrate each other, the energy to do that is up to infinity. You can also so code, for example, surface polymers, and if you dissolve these particles in the solvents for which solvent is the best solvent for the polymer, these brushes want to solve into each other. They want to overlap rather than being the solvents. And then you try to manufacture forward, which is very short range, the range is about the type of polymer. And then you get what people call an adhesive or finish layer. And you can also charge them, so you can have surface charge attached to the surface of the soft colloid. Then you have, of course, the Coulombic-like repulsion between these particles. And I'm going to talk about these kinds of interactions in an electric field. And these things, depending on the potential, you can have a lot of different phase positions, like liquid, dark, crystallization, etc. You can also have aggregation in gels, for example. There's a whole range of different states and phases you can form, depending on what kind of interaction potential you can choose by managing what you have on the surface. Okay, so I'm going to talk about the charged particles. And the charged particles have connected to the surface. For example, the countercharge group, which can split off an H plus. So here is the CO8, and this H plus can go into water, into the solution, and then the surface becomes negatively charged. Now, the first question that you would ask, what is the equilibrium state of such a particle in the solvents? Now, of course, you want to minimize the free energy, the Helmholtz free energy. And you can do that by minimizing the internal energy, maximizing the entropy. So there are two implications. The one is that you dissociate all the groups where the H plus vanishes to infinity. Of course, that makes the internal energy of that state very large because you have to separate the plus charge from the negative charge. But it makes the entropy, of course, high because the ion can probe the entire volume. And so this is high, so that is unfavorable. But the entropy is high, so that makes the thing small. But of course, there's always a kind of trade-off between the two. So the other extreme is that these are not dissociated. And then, of course, you have a very low mu, actually an electrostatic energy equal to 0, because you don't separate positive from negative charge. But of course, the entropy is very low, because the H plus are sitting on that group. And of course, what happens is something in between. So you will have a plus ion, which dissociates from this group, but they won't disappear to infinity. They are attracted by the negative surface and form some kind of a positive cloud around this particle, which is called an electric double layer. So the situation is the following: we have, for example, a negatively charged colloidal surface, and then you have this H plus ion here. So we have a cloud of positive charge around this negatively charged colloid, with an extent which is called the bio length or the bio screening length. And that length decreases with increasing salt concentration. So if you add iron from the outside, then the extent of the cloud of the positively charged double layer is called will shrink. So add salt, and this length, the extent of the double layer is decreased. So that will be important, what I'm going to tell afterwards. So this is the electric double layer. You have additional phenomena, which is called ion condensation. So if the current potential is very high, you'll also have a layer of condensed ions. So a layer where the concentration of the positive ions is very large. And this is very thin, relatively thin layer. So we have two types of distributions around the color of the screen. We have a positively charged thin layer with a high charge density for the condensed ions, and we will have this diffused electric double layer, the extent of which will decrease with increase the cell concentration. Okay, so what I'm going to talk about now is rod-like colloid particles, which are highly charged. We take a deep-bodied particle as a model system for rod-like colloid charged particles. So these are rod-like particles which have a length of about a micron. So the thickness is about 7 nanometers, so they're very long thin. And the thickness length is 2.5 times the contour length, so they are pretty stiff. So they typically bend a little bit, but not much. So it's a good model system for a rod-like colloid. So this is a divided particle. So this is the DNA strand, the double stranded DNA strand. On top of which you have 2,700 proteins attached to the DNA. And this leads to a very high charge density on this rod. So you have approximately 9,000 elementary charges on this rod. So that means that every 10 nanometers, in every 10 nanometers, you have an elementary charge. And that is so highly charged that you have so-called condensed ions. So there's a question then.
What virus is this? Say virus. What kind of virus is this?
This is a virus that causes diarrhea in pigs.
Okay, it's not the vehicle.
No, it's completely. So it's not dangerous for people. I mean, you can principally eat it and not like it. Otherwise, you don't use it properly. Is that the answer?
Yeah.
Okay. So here you see the proteins. So you have a condensed layer of ions, and on top of it, electric double layer. And if you look closely, you see here these proteins, and they have a screw-like structure. So that means it's like a screw. If you put two screws close to each other and force them together, they tend to make an angle. And that happens here too. So you have a phase transition and local rotation, where each orientation of rod is equally likely to occur. That is the hypertrophic state. And at the high concentration, due to the interaction between the rod, they align along certain preferred direction. So here there is an alignment of the rods with the interaction between them. Now, as these rods are close together, they feel this twitch. That's because of the chiral structure, this screw-like structure of the surface. And so they make a twitch, and then you get the so-called chiromagnetic. So this vector will propagate the state like this. Right? And that's why there's EPG polarized. If you look at the solution, you will see this right. So that is due to the helpful core structure, but you only see the structure if the ionic strength is high enough, so the total strength is high enough so that the thickness of the double layer is small enough so that the rods can approach each other, so that they feel this 15 force. If the total concentration is low, so the extension of the double layer is large, so they repel each other over a large distance, and they do not come sufficiently too close to make this fluid-like interaction. So for low constraints, for local concentrations, you see an pneumatic, which is the bright area. This is a picture between both polarizers. You see alignment because the rods are biofinish. So bright areas are pneumatic, and as soon as you increase the ion strength, you have a transition between the normal pneumatic and the carbon pneumatic where you see the stripe. So the dark area here is most of the time isotropic. So we are going to talk about the system, which is in the two-phase coexistence region, where you have a coexistence between an isotropic phase and a pneumatic phase. So this is a pneumatic domain floating in an isotropic environment. So this is within the two-phase region, isotropic pneumatic. Not all the experiments are done at a low ion strength, where without the fields, the pneumatic state is a normal pneumatic, so a non-carbon pneumatic state. The biolayer is about 27 millimeters, which is much larger than the thickness of the core. Okay, so now we are going to apply magnetic fields. The experiment, let's put this sample. So you take two electrodes here, and the sample is here in between, and you have two polarizers, a light source, and you look at the image. This is how you obtain this image. So it's the black is isotropic, and the light area is pneumatic. So this is how the phase diagram looks like. So this is the electric field strength, volts per millimeter, and this is the frequency of the field. And you see a number of phases. Now at the zero field, you have this normal pneumatic in equilibrium with an isotropic phase. But if you apply an electric field, you will induce different phases. So let me explain which phases those are. As I said, this is the normal situation without the field, called the N from pneumatic, but in equilibrium with isotropic. And then if you increase below this frequency, you increase the field strength, you also going to get a current pneumatic. So for some reason that the ion strength is increased so that the rods will closer together, your field is switching forward due to the groove-like structure of the surface. And then it becomes current. I will explain why this happens in a moment. And then if you go to high frequencies, it becomes all of a sudden isotropic, or let's say non-homogeneous or homogeneous. And the rods here are aligned along the electric field. So you align the rods, and that is called the homogeneous alignment, so along the field. And it's called homogeneous, so you get rid of the domain texture, it becomes all homogeneous.
Yeah, these are optical images, or the Fourier
images.
directly from the microscope. Okay.
Yeah. So in the field of view is about 400 microns. So it's a very simple experiment. Right? So you put two electrodes, which are transparent, and you put them between both polarizers, a light source to it, and you make it unicord image.
So the stripes you see are bundles of the virus.
Well, so this, for example, is so a domain where the rods are pneumatic. We have the third alignment.
Okay. Yeah.
And because we draw by a fringent, so the reflective index along the rod and perpendicular to the rod so are different. So it will return the light.
Yeah.
And if it is isotropic, there is no preferred alignment. So you would see that so it's dark because it corresponds to polarizer. So there is no light coming through if it is isotropic. If it is instantematic, because of the bifringing of the rods, the polarization direction will change. And then you will find over finite so intensity. So everything that is bright and to prefer to direction. And most of the time, I was thinking I have a problem.
Okay, no, but in the other, you see the stripes.
Yeah.
So what are the stripes?
Well, that is for the countermanic tail, where the vector make a turn like this. Right? And of course, if it so happens, the case of the vector, so the preferred direction of alignment is flipping out of the plane. And of course, there is no return to polarization direction because we're moving on top of the thing. And then it will be black again. So if you look like this, so from the top of this, so this vector, and then the light is going like this, it will look black. And then if it turns, it will go bright. And then it turns further, it will black again. So if you look at this picture again. So here, the third direction of orientation in the black thing, then this numeric director, the direction of preferred alignment is sticking out of the plane. And here it lies inside the plane. Yeah. So this is due to this turn of the numeric preferred direction.
At the point where the red, blue, and yellow lines meet,
Yeah.
do you have a critical point?
Yes, so I'll come to that.
So do you see fluctuations?
Yeah, so there is here, so if you approach this point in any direction, you have a length scale that diverges, and you have a time scale that diverges. So fluctuation can become very, very slow. But I will talk about it in a minute.
So the final question is, if that is a tricritical problem.
Well, you will have three surface lines to come together.
Yeah.
So you could call
That would be a tricritical problem.
Yeah.
Could be.
Yeah. So I will show a little bit more about this point later. So on increasing here the field strength, the normal numeric turns to a counter-numeric. And that's one explanation would be that when applying the field, the ambient ionic strength increases. The reason for this I will explain in a minute. And then so here at high frequency you have this uniform state that the rods are aligned along the field. And then, so you can show that for frequencies higher than about this frequency, there is no charge polarization anymore. The frequency is too high because the dyes cannot follow the field anymore. So you don't have a polarization of the double layer and the layer of condensed ions anymore. So dipole interactions, if you like, are not important here, are absent. And the reason why you still get a different phase, I will explain that in a minute. Now, the most interesting thing is that if you go along this line here, you will enter a so-called dynamical state where these numeric domains melt and form all the time. Now, of course, this is a static phase, so it doesn't change in time or hardly. But as soon as you cross this line, these domains melt and form. And I'm going to explain in a minute why that happens. And in fact, so the time scale on which melting and reforming of the domains appear has nothing to do with the frequency, but it has to do with the distance from this transition line. So if the distance is large, so the time scale is short, so they melt and form very rapidly, and this is real-time moving this one as well. And you see as you approach this line, the dynamics becomes very, very slow. And in particular, in this point, you will have a critical behavior in the sense that the domain size, the average domain size that you find, diverges to go to this point. And also like here, the time scale which this melting and forming occurs also diverges. So in that sense, you could interpret this as a type of non-equilibrium empirical point. And you can actually measure the critical effect from exponent, which we did. But I'm not going to talk about it. So we have these two regions where the polarization of the double layer and the layer of condensed matter is formed. And you have so this region where these polarization effects are absent. So the question is why that the why is the homeotropic effect performed? Well, we think that that is due to electromagnetic flow that is induced in the double layers and in the layer of condensed ions. So you induce additional hydrodynamic interactions because the field acts with forces on the ions in the double layer, and these forces acting on the ions are transferred to forces on the fluid, and the fluid then starts to flow. That is called electromagnetic flow. And this extra flow, of course, translates in extra interactions to this electromagnetic flow. And we think so that must be the origin of the stability of this H-phase. But we don't really have a theory for that. That's very, very complicated. Now, as I said, the transition from the angle and star phase could be explained if you have a mechanism by which, by increasing the electric field strength, you increase the ambient concentration of ions. And because the thickness of the double layer decreases, then the ionic strength in the solvent will increase. And so one mechanism that should explain this is that if this is your rod and you have this condensed layer of ions, then, and this is the direction of the electric field, then of course the positive ions, which are mobile in the condensed layer, will be pushed upward. So here you have a high concentration of H+ ions, which is higher than the rod would like to have. And as a result, these ions will go into fusion. And the opposite happens here. Here we have so a shortage for H+ ions. So here there will be an attachment. So a transport of H+ ions constantly into the rock, into the condensed layer. But this is of course much slower, so the ion has to go from far, whereas this is much faster because the ion should simply disappear out from the condensed layer of ions. And these ions then increase the ambient systolic concentration, and that then gives rise to this transition from the pneumatic to the carbon. So the biolayer will decrease, and they will feel this like interactions. So of carbonation or structured form, you get to start. Now we try to explain the dynamical state. We try to make a theory that is based on the Coloquio equation, which is well known here. So this is the equation of motion for the position coordinates of the rod, so n rod, and the orientation of the rod. So U is a unit vector along the long axis of the rod. And the probability density function has two contributions. There is the change of probability into translation motion. So this is the translation of the diffusion coefficients. This is so the friction coefficient for a rod, of course, depends whether it will go long axis or perpendicular to it. That so comes from this term. This is the fixed friction, fixed wall, and then you have the forces. So this is the total interaction potential between the rods, so including the electric doublet in the core. And this is the total force of the electric field on the core of the column. And then you have the rotational distribution. So this is again fixed wall, but then for rotation. And you have the torque on the rods due to torque on the rod due to the external field. What you would like to have in the equation of motion for this orientational order parameter, which is the average of the dynamic product of two units of a given rod. And so you can obtain, so you have to integrate this whole thing over all the position coordinates, then this will disappear into God. And the integral over these things, you have to form as well. And then you get, if you multiply this for first by u, and then you integrate, it's effect of everything except one, you get either one and one. And so you have to do the integral. And then we see hardcore interaction. Interactions to the double layer, interactions to the polarized layer, condensed ions in the polarized double layer. Then you assume that the orientation of a rod hardly changes during the cycle of the electric fields, which is the height. We use one type of approximation for the percolation function, and you do a peaceful line expansion to fourth order in the shorter parameter, in which you get this equation for the action. So if you want the identity for the isotropic phase, and it has a different form as soon as you have pneumatic. And then the largest eigenvalue that then will give you the degree of alignment in the pneumatic. Now you have a number of terms. This is the ideal term for non-interacting rod. This is the term that describes the interactions between the rods where you have the effect of interactions due to the double layers. You map that as an effect of hardcore, so the envelope, which is given by this equation. So this is the effective thickness of the core that also takes into account the repulsion due to the electric double layer. And then you have so a twist effect, and that is the effect if you have two rods like this, and you put them together, and when they have the same alignment, of course, the interaction energy is very, very high because you have an enormous overlap of double layers. So we try to minimize the interaction energy by making it so a twist. Then you decrease the overlap of the double layers and thereby the energy. Right? So that is the twist factor. And then you have to turn which has to do with the interaction between the dipole, and you have the torque contribution into the torque that the electric field exerts onto the core of the rod. And unfortunately, if you solve this numerically, there's no dynamical state. So you do a lot of work, you don't find what you want to find. And so we came up, so what is not included here is that you peel off ions from the condensed layer of ions. And then so you have this association, dissociation. So this effect is not included there. So how could this affect, if you peel off ions here, which disappear into fluid and then increase the ionic strength. How can you explain that gives rise to a dynamic state? This is the only thing that is not in here, so that should be at the origin of this dynamic state. The explanation is as follows for the existence of the dynamic state. So let's start here. So these are two rods, and you have to think of this as a pneumatic domain. So millions of rods that I draw into. So this domain is a line. That's starting to get the situation. Then you have this peeling off of the dislocation of condensed ions. So this dotted line here is supposed to indicate the thickness of the electric double layer. So you peel off these ions, and then the thickness of the electric double layer will decrease. And because you increase the total concentration in the solvent. So the effective thickness, the effective concentration of the rod will therefore decrease. And it will decrease to an extent that the concentration, the effective concentration is not high enough to stabilize the pneumatic state. So the pneumatic state will become unstable and the domain will melt. So it becomes isotropic again. But as soon as it becomes isotropic, then you will have a reassociation of the ions, and the rod will approximately attain the original state. That is to say, the ions will associate, and then the ionic strength will decrease, and that will increase the thickness of the electric double layer. So that will give rise to an increase of the effective concentration and make the isotopic phase unstable. So a domain is formed, again, a pneumatic domain, and that domain is oriented by the external field, and you start again. So this is the cycle that would explain the dynamic state. And you can actually incorporate a model for the association and dissociation into the small toxin equation. Not going to show here. But then you need to find the cyclic state. And you also find from that, for example, if you go to this transition line, that the dynamics becomes extremely slow. But I'm not going to show you that. So the conclusion from this is that there's a dissociation and association of condensed ions is essential for the transportation system. The end-to-end star then is due to the associated increase of the ionic strength, and it's also explained in the part of the stability of the dynamic state. And at high frequency, so here it's essential that you can polarize things, right? That is necessary to peel off the condensed ion. But at high frequencies, you cannot do that anymore. And the hypothesis is that the formation of this uniform homotropic state is due to high dynamic interactions to electrosonic flow. Now, I'm going to use the same system to look at the information of the glass. So we found, so Kyong actually found some glass condition in the system. So this is the phase diagram for a given low salt concentration. So we have a thick electric double layer, 27 nanometers. And we have you have here, so you have the isotopic state. Then you have here a binary, spinal. So this is called the region between where you have an equilibrium between isotopic and pneumatic, to which we apply the electric field. And then here you find that resistance if the concentration is high enough, even though you have a low salt concentration, if you increase the concentration, the rods will nevertheless come closer together, right? And that will then give rise to transition from a non-pneumatic to a diapneumatic. And then if you go even further, you find here a glass condition. Now let me explain how we found it. So we are going now to look at the same kind of pictures as before, we both polarized. Of course, without an electric field. And you simply take that so cuvette from the line, and you put it between these four polarizers, and you move what happens. Now I'm on the next. We see, so I'm first going to look at the concentration of 11.1 milligram per mil, which is relatively low this concentration. And I'm going to look at 12.3, which is just above. So there is only a small difference, but the behavior is completely different. So you fill the cuvette, you put it between these polarizers, and you think what happens. And this is what happens. So we start with an aligned phase, because it's really important when you fill the cuvette. But then there is normal transition to thermodynamically stable to thermodynamic state, which is here. And this experiment takes for 8 days. So you have to wait for a long time to see this. Let's see where you can see where we are. No. So now we go to this little bit high concentration. And this is over the total 8 days. And in the beginning, you see nothing happening. So 4 or 5 days long, nothing happens. But then, what happens is that over here is the engine is called cuvette. And of course, there's also a little bit of evaporation of trouble. And that causes gradients in the pressure. And at some point, these pressures are so large that this structure starts to melt. So this is actually a glass that I was showing in. And it is gradients in the so you see from this side, you have this perturbation that you can at the edge of the destroyed the entire glass. It has nothing to do so with science, it's just my picture. So it takes about 8 days to see from there. And then it's destroyed the entire glass. Now, how could you so characterize the dynamics of such a morphology? Because the way to do this is to construct image time correlated function. So you have a CCD camera with hundreds of pixels. You measure the intensity of a pixel times t. You subtract the average over the whole chip. Then you multiply that by the intensity times t is 0 minus the same average for intensity over the entire chip time t is 0, and then you normalize it to 1 times t is 0. And then you average over all the pixels. And then you get what we all call video image time correlation functions. And this is, for example, which is really at a very low concentration, so far below the glass condition. And you see directly after filling the cuvette, you see a very fast dynamics. Then if you wait for 20 hours, it is already that fast, and that's about 170 hours, that is 8 days. You reach the equilibrium state. And of course, there are still some texture dynamics. It's in equilibrium system. And this is 11.1, so just below. You see the same thing, relatively steep decay still after so equilibrated. So the texture has its own sort of dynamics. But then the robust glass condition, starting from time t is 0. They are all the same, and there's a kind of aging, if you like, but it doesn't involve time anymore, independent of the waiting time. So the so you can measure this slope, the final slope that gives you a relaxation rate, and so gamma in 1/4. And you plot that at the point of concentration, and you see it's almost gone to zero. Then you see so a sudden jump to very low value. So that is clearly transition of the morphology, and that is a glass transition. So this goes to there, this is from the movie, and this is unchanged. So you see the jump, and you interpret that due to a glass transition. Yeah.
Yeah, that looks like a fractal structure.
So this one here,
Yeah.
yeah. But this is really due to the fact that if you fill it with red, then it flows and you align the rod. So it depends on how you fill it with red. So I don't think that this structure has a particular meaning. Now to verify whether this is really a glass condition, we can do it for dynamic light scattering. So you measure the dynamics of single particles, the dynamics on the particle level. And there you see also, if you increase the concentration, you see that this is also frozen. And that also so this is the decay rates here, but now obtained from the dynamic light scattering. So you look at the dynamics of the single particle, and that is from the second time scale. And you see that the decay rate goes to zero at exactly within experimental error the same concentration. But the particle dynamics freezes at the same concentration where the texture freezes. And that makes almost sense because if the particle dynamics freezes, so the domains become larger, they become solid. And of course, then also the dynamics of the texture will stop, freeze. That is the intuitive explanation why you find freezing of the particle dynamics and the texture dynamics that freeze at the same concentration. And the reason laag is so the laag in this case due to long range electrostatic interaction. Because you are at low levels, when you increase the concentration, you diminish the extent of the biolayer. And then at some point, they do not form a glass anymore. So the glass transition is really due to a long range electrostatic interaction, and that is called a weak glass.
Yeah. What is the index P and E images?
What is
GE.
Well, that's a good question. So this was a long time ago. So this is, I think, the electric field autocorrelated.
Okay. Yeah.
And what is this is normalized. So this is normalized.
Okay.
And this is
I see.
and this is normal. And this is also a difference in waiting times in both concentrations.
And then that was another question, because it doesn't seem monotonic. Anyway, maybe depend on it.
Yeah, so this is still below the glass of the concentration. So they will also always decay.
Okay.
But this is above, you see that the gold. And all these are below, and you see this increase in the realization time.
Okay.
Which goes to zero at the same concentration where protection. So that's what I wanted to tell you. Thank you for your attention.
Okay, it's time for questions. So, yes.
Can you go back to the slide where you show the glass transition as you increase the concentration?
So you mean the movie?
No, it wasn't that.
The big one?
No, the other, like that, that's like, I the phase was electric field versus frequency.
Yeah.
So you did the same measurements and got different phase diagrams for each from the
Yeah, no, so that, I didn't say that clearly, I think. So there's an electric field in all direction. So this phase diagram,
Yes.
that is at one particular flow concentration and one particular FD concentration. So this diagram is for one particular FD concentration, so one single concentration, and one single flow concentration. So the FD concentration is fixed, and the FD concentration is equal to the FD concentration is here. So all the experiments with the electric field are done for this concentration.
And then, well, then here comes my second question. When you increase the volume fraction, does the phase diagram changes completely?
That's a good question. So you can change the two things here. You can change the flow concentration and keep the FD concentration fixed, for example. And then it looks completely different. Because if you change the flow concentration, you change the ionic strength, right? So if you add salt, then the extra salt concentration due to this dissociation of condensed ions is very, very small as compared to the salt that you already have. And then it will have no effect. So you will lose all these conditions at higher salt concentration.
And for
for lower salt concentration, this will be enhanced. Now it's now it will be lower. There is actually thing to tell. So if you decrease the salt concentration, so actually we did that, but so I think this will increase. No, it will decrease because the effect of the dissociated ions will be larger if you put in by hand less ions right from the start.
I'm not sure about.
So this will probably go down.
Sorry.
Yeah.
I'm not sure if you did this experiment, but I think you only increase or between the ion concentration, you only get a hit on your finger.
Yeah.
That's it.
So I will look it up in the paper. That was some time ago. So we did these experiments at different salt concentrations just to verify whether the electric, whether this mechanism, so it's really true. So if you add a lot of salt, it should all disappear, right? Because the extra contributions from the dissociated ions will not matter. Is that clear?
the thing is that I cannot hear you very well.
So we did these experiments also by higher salt concentration to verify whether this mechanism that we propose is correct or not.
Okay.
And if it is correct, and you increase the ambient salt concentration by hand, so by adding salt, then this phase diagram could disappear. Because the contribution to the ionic strength from the dissociated ions will become so small that it doesn't have an effect anymore. Right? Okay.
I think. Sorry, thank you, guys.
Do you remember when you obtained the yellow line? If this is the second order transition, did you see fluctuations along the yellow line?
I think it is of second order because the structure, so the microstructural order in the phases is completely different. Huh?
Yeah.
So it should be
Yeah, the red line or blue lines are first order.
Yeah, the first order is for sure.
And the yellow line might be a second distance.
Yeah,
If it's a second distance, then you have triangular point.
yeah, so I think, so this is second order.
Second order.
Yeah,
Yeah, then you have a triangular point.
yeah, okay, yeah. That's true.
Los chates, si no se animan en inglés, pueden preguntar en español y lo traducimos.
So
Okay,
what's the
ahí.
question?
We did something similar study with this model system. And when we increase or decrease our concentration, we only get a shift in the phase around. That's it. Because of higher concentration, the polarization and all the mechanism involved in this AC field effect only shift this.
But that is probably a different system where the dissociation of ions is not so important, I guess.
Yeah, and we got the dynamics of the system and the shape of the system. So
Yeah.
I'm not sure if you verify this in some experiments, lower or higher concentration.
Yeah, so we have done this at various concentrations. But of course here, as compared to your system, I think, so here it's very important that the ions dissociate for the condensed layer. And that is by many systems, of course, not so important. And that makes so the change of this thing more than just a shift, I think. Okay. That we should maybe discuss that now.
Magdalena.
Yeah, with respect to this glassy phase, and you said that it's a different glass phase due to the electrostatic repulsion. And if that is the case, the orientation is important. They become glass, but aligned in them, or they might be found oriented.
Yeah, so what you So what you actually freeze in is it's a chironomimetic structure. So the glass will be a chironomimetic.
Okay.
So you can maybe see that from
This orientation will become
one.
this orientation will become persist in the glass.
Yeah, so it's still there in the glass. You can maybe show if we wait long enough for this movie to finish. If it starts. It's the best thing about this movie, you never know when it starts. Well, no, wait a minute, I'm so wrong. So what I wanted to say, I mean, so you're right. So I mean, it's difficult to say whether the glass is still a chironomimetic, because we do these kinds of experiments where you have to destroy the orientational order in equilibrium due to the fact that you shear the system by filling the cuvette. So it will freeze in so in a texture, so in a structure that exists after filling the cuvette. Right, and I don't know whether that is still so a chiral phase or not. Okay. So I'm not sure whether the glass will be chiral. So that's the answer. Yeah.
Now that you're showing this image, what was the preparation for what did you use the experiment before you start recording?
Well, you simply should take a pipette. So you suck up the suspension, you put it in this cuvette, and you put it between the two polarizers, and you watch what happens. So it's a very simple experiment.
The current pneumatic is a liquid crystal, and the other one is not a liquid crystal, right? It's the soft.
Which one do you mean?
The glass conclusion works.
Well, of course, if you're below the glass, this is of course so aromatic at the end. But in the glass, due to the filling of the cuvette and shear everything away. So you don't exactly know what kinds of stuff you have. So that is not a liquid crystal. But this is of course, so this is below. And you can maybe see the stripe if you carefully. You can maybe see the stripe for the aromatic stuff. But this is of course below the glass.
You had the line effects there.
Yeah.
No more questions. Okay, Magdalena, you want to say something?
Yeah, can you check if somebody?
There is no question from the.
Were connected by Zoom.
No, there is no questions.
Okay, good. Yeah, I would like to say that we are very happy to have Dhont and Mary here. And I think we will have a good time meeting
I'm sure.
with us the next 2 days. Also, if any of our colleagues want to have a chat with them at some point, tell us schedule some interviews with both. And also, we are very happy to be with you in this celebration of these 40 years of collaboration and friendship. And I think that it has been very enjoyable for many people in our community and we in services in particular are really happy.
I would say for me, it's a big honor to be here, and a big honor to be able to make this tour, where you entertain us and we talk science. So it's all very nice.
And can only say.
Yeah, good.
Okay, well, thank you, Greg. All right, so.
By the way, estamos invitados todos mañana en un seminario pasa a cargo de Diana Meyer y también porque han utilizado. Igual a la hora, sí, aquí mismo, sí. Bueno, ya.
Más abajo. Gracias.